Hello everyone, this is the lecture on analog and mixed mode VLSI design W638, and this right now we are doing basically a digital circuit design topic from the chapter 2, basically a submicron circuit design. In this till now I have covered the submicron CMOS process flow, capacitors and resistors, current mirrors, digital circuit design. In this particular aspect I have covered basically um, the basic crystal or the Boolean function realization, then some combinational circuit. We have discussed how to realize those circuits using CMOS, right? So those things are already covered. So today I will start our discussion from basically switches. At this point, adders and basic logic circuit designs are already covered. So let's start with switches. And the switches, first I will cover the sampling circuit. This is the somewhat sampling circuit. So before discussing this particular aspect, I will take you through the basic concept behind the sampling circuit, right? Sampling and basically holding aspect of the sampling circuit, right? So let's start with, say for a particular sampling, as name suggests, first of all, I want to tell you that I don't have a stylus right now, so writing them from mouse is quite difficult, and I hope you can cope up with this and try to understand whatever I'm trying to write. Okay, so let's start with the sampling circuit. So in the sampling circuit, you can say you should have a switch which is used for the sampling aspect, right? Then there should be a capacitor. This capacitor will act as a holding capacitor, right? So in this, basically this particular terminal can be assigned as a Vout, output voltage. This will be assigned as Vin, where the input voltage is applied. This should be the switch, and this should be the capacitor, which is generally defined as holding capacitor, right? So say if there a particular pulse is applied to this particular switch, right? Considering when the positive pulse is applied, right? Say this is 0. When the positive pulse is applied, this switch is on, right? This means the switch is shorted. So under those conditions, whatever input is coming from this particular terminal will be stored in this capacitor, right? Will be stored in this particular holding capacitor, right? So when the pulse is down, so at this point, this particular switch will open, and under the condition of when switch is open, whatever the charge is transferred from input terminal to the capacitor when the switch is on is holding by this particular capacitors. So same charge is present at a point when the switch is open also. So this particular circuit defines a simple sample and hold circuit, right? So in this circuit, if we want to realize using MOSFETs, so simplest way is to remove or replace this particular switch by using a simple MOS structures, right? For that aspect, say let's replace switch with a simple NMOS circuit. So in this NMOS capacitor, say the switch is replaced by NMOS capacitors and remaining things are same. Say there should be a holding capacitor, right? This is the holding capacitor CH, and this should be the output terminal. This should be the input terminal. This should be the gate voltage. So from the basic mechanism of the MOSFET, when a particular gate voltage is applied, basically so that it can create a channel between source and drain. Under those conditions, this particular MOSFET will act as on switch. Basically, when the gate voltage is more than the threshold voltage, it creates a channel and it is on switch, right? and when the gate voltage is below that particular threshold voltage, there is no channel and this particular switch will act as open condition, right? So the when switch is on, whatever charge is present at the input terminal will transfer to this particular holding capacitor, and that particular charge will store here. And when this MOS structure is off, so whatever charge is stored during when this particular transistor is on is stored here. So the same value is present for both the positive and negative sides, right? So this is the simplest structure. But as we know, when the transistor is on in, say, the triode region, or in the you can say saturation region, in both the regions there are some finite resistance present in the circuit, right? So as we know somewhat the characteristics of the MOS output characteristics, basically uh, those are like this, right? And I hope you remember that this is what called saturation region, this is called the triode region. So in the triode region the resistance is almost linear, and this region the resistance value is quite high. So overall there is resistance present. So under these conditions, say let's say first write the equation for the resistance for this particular MOS structure, considering all the parameters, say mu n, Cox, W by L for the structure and all those things. So the relation for resistance can be written as mu n Cox, right, W by L into what should be there, VGS minus VT. In this case, what should be VGS? VGS should be VG minus V input, and the maximum voltage in VG here the clock pulse is applied, right? So from the clock pulse this maximum value should be VDD, right? So considering VG as VDD, we can have, right, VDD minus of the second term should be what? V in input voltage, right? This will give you the equivalent value of VGS minus of threshold voltage VT. So this gives the equivalent resistance for this particular MOS structure. Say let's draw the equivalent circuit of this particular MOS structure. So let's take another color. So for this the equivalent structure can be drawn as, there is some resistance present in the MOSFET region, there is a holding capacitor in this region, this is the V out voltage, this should be the V in voltage. Okay, so let's discuss one more thing before going ahead. So in this, basically for a particular MOSFET, when you are biasing something, right, when we bias a particular this MOSFET, we have applied a certain value of VG, right? So VG is VDD, the maximum value, which is almost fixed for the, say, condition of when the pulse is high. But VI, this is the input value. This can be changed, right? So in this, if input value is changed, right, effectively this particular term will decrease. If this term will decrease, you can say the resistance will increase. This can also be related to, say, in this particular plot, say here in the output characteristics, output current should be ID and this should be VDS. So in the general equation of the current, I equals to mu n square W by L, here is VGS minus VT, right? Here VGS is what? VG minus VI. So if VI is increasing, VG minus VI is decreasing. If VG minus VI is decreasing, effectively current will decrease. Then the similar analogy, if current is decreasing, you can have more resistance, right? So in this circuit, you can have the variable resistance for the MOSFET we have used, right? So this resistance should be variable, which will vary with the applied input voltage, right? So from this analysis, uh, can we comment on the input voltage or the boundary conditions? What should be the minimum input voltage so that this minimum or maximum input voltage, basically the boundary input voltages for which this particular MOSFET will work effectively and give the required results, right? So for this, the condition should be, say, V input is if greater than V Dd minus of Vt, right? So if this condition is satisfied, by simple analysis you can think of, if this value is Vdd minus Vt, Vi is greater than this value is negative, so it will not create a charge. So we, somewhat in the simplest way, you can say that this will basically take the MOSFET into the cutoff region. So this will not act as a switch. So under those circumstances, this will act as a no. This is basically considered as an off state when this condition is achieved. So this will not transmit at this time, right? So to ensure the transmission from input terminal to the holding capacitor, the value of input should be less than this particular value, right? So in this, basically when we increase the input, we are effectively making our transistor to go into the cutoff mode. So the basic working of this particular MOSFET will not work, right? So for that aspect, we get the maximum boundary condition for the input value. What can you think of, say, the maximum value relation? What should be the, and is there any say boundary for V input for lower value? Yes, should be or it should not. So for this case, let's say if V in value is smaller, if V in value is small, the effective resistance should be less. If effective resistance is less, you can say it will effectively act as a better transmitter or better on switch, right? So for the lower input values, it will not affect the working. The similar analogy we have discussed earlier, that NMOS is basically a good transmitter of low values, while PMOS is uh, basically hold the good one value or the high values, right? So similar analogies here. Vi input value of Vi, basically Vi is if small, it holds good and it can transmit easily, while so NMOS is effectively transmitting 0 better. And if we consider the case of PMOS transistor, there should be a lower limit for the MOSFET work, right? So we will discuss this later. So before that, so in this particular RC constant, right? If you are considering RNC circuit, equivalent circuit for this particular NMOS structure, say if we apply a sinusoid at the input, say if this value is a sinusoidal signal, there is a sinusoid signal over a DC value of V dd by 2, right? So there is an AC value which is over the DC value of VDD by 2. Under this condition, what will happen? Say in this circuit, if we have discussed till now, if the value of V in is increasing, if V in is increasing, the resistance will increase, right? If resistance is increased for the RC circuits, bandwidth is somewhat related to 1 by RC. So if R value is more, you can have less bandwidth. If R value is more, you will have less bandwidth, right? So with increasing RC, there is a possibility of larger distortion. And for the smaller values of V input, you can have smaller values of V input. Uh, Resistance should be less. So if resistance is less, right? If resistance is less, bandwidth should be more. So the uh, signal will transmit good if the value of input voltage is less, input sinusoid is less. So somewhat when the input is transmitted through these particular circuits, you can have at the output there is some phase distortion, right? This should come closer, this should vary less, and this should vary more. So somewhat you can say if it varies something here, the distortion should be less. If you move upward, distortion should be more. If you move downward, distortion should be less. Here, distortion should be less as value is decreasing. If you move upward, distortion should be more. So, somewhat you can understand that with varying input signal with the sinus, which is sinusoid, you can have uh, some nonlinear distortion in the circuit. This is because this particular resistance is nonlinear because it depends upon the input voltage. So whatever we have discussed till now, from this we can say if we are using NMOS circuits, we are getting some issue, right? So nonlinear distortions. So what will happen if we use a PMOS circuit, right? So what will be the change? Just in